Hello everyone, I'm Zeng Cheng. We'll study the last part of this course together. In our course, lots of mathematics will be involved. However, math is just the same as words. It's a tool to express ideas. Therefore, in our course, I'll try as much as possible to show you the ideas expressed by the mathematics to you. Hello everybody. In this lesson, we're going to study system function and its frequency domain characteristics. Similar to the analysis of time domain characteristics, we'll discuss the relation between the system function and its frequency response based on the zeros and poles of the system function. Here, we'll mainly focus on the continuous LTI system to analyze the relation between its zero pole points and its frequency response. And then the relation between zero pole points and the frequency response for the discrete LTI system will be introduced briefly. First, let's take a look at a continuous LTI system that satisfies both causality and stability. The necessary and sufficient condition for a continuous LTI system to be causal and stable is that all the poles of its system function should lie in the left and open half of the plane S. In this case, the frequency response of the system can be obtained directly by replacing the S in the system function with a j omega. So we can get the system's frequency response h of j omega from a system function. The modules of h of j omega is the amplitude frequency response, and the phase angle phi of h of j omega is the phase frequency response. From this result, we can see that both the amplitude frequency and phase frequency response depend on the zeros and poles of the system function. And how will the zeros and poles of the system function affect the frequency response of this system? This is the question we'll be discussing in depth below. In order to analyze the relation between the zeros and poles of the system function and the amplitude frequency and phase frequency response, we can introduce a so-called zero vector and pole vector. Take an arbitrary point j omega on the imaginary axis of the plane S. We call the vector which is from the pole pi to it the pole vector of pi, where ai is the module of the pole vector and theta I is the phase angle of the pole vector. Therefore, we can express the pole vector as a form of modules and phase angle. Similarly, for the zero zeta j, we can build its zero vector. When both the poles and zeros are denoted as vectors with module and phase angles, the frequency response of the system can be accordingly converted into a form expressed by module and phase angles of zero and pole vectors. Then, the modules constitute the amplitude frequency response of the system, and the phase angles constitute the phase frequency response of the system. In such a frequency response, j omega is a variable. It will slide along the imaginary axis j omega. With the variation of omega, the module and phase angles of the zero and the pole vectors will vary accordingly. Thus, the amplitude frequency response and phase frequency response of the system will be bound to vary with omega. Based on this principle, we can also analyze how the amplitude frequency response and phase frequency response of the system will vary with the omega. Next, we'll focus on how the distribution of zeros and poles in the plane S will affect the amplitude frequency response of the system. Firstly, if all zeros and poles are far from the imaginary axis, then as omega slides along the imaginary axis, there are no obvious changes on the modules of all zero and pole vectors. In other words, with the variation of omega, the amplitude frequency response of the system does not fluctuate much. At this time, we'll get a system with a rather flat amplitude frequency response. Secondly, if a zero is very close to a pole, such as the pi and zeta j in the left figure, or they are mirrored about the j omega axis, then with the variation of omega, the module of these pairs of zero and pole vectors will vary equally, or nearly equally. Thus, the ratio of the pole vector modules to the zero vector modules is almost equal to 1. Then the effect of this pair of zero and pole on the amplitude frequency response are trivial and almost can be ignored. Thirdly, if a pole is very close to the imaginary axis, such as this pi, and there's no zero nearby, nor exists a mirror zero, then when omega slides near this pole, the modules of the pole vector will approach to zero. Hence, a peak of amplitude frequency response will appear nearby this omega. The fourth case is similar to the third one. If a zero, such as this one, is very close to the imaginary axis, meanwhile there is no pole nearby nor exists a mirror pole, then when omega slides near this zero, the zero vector will have a very small module. While for other omega values, the vector module of this zero will not be too small. Therefore, there will be a valley of amplitude frequency response at the frequency near this zero. We can demonstrate the results above further with the following examples. This is a system function with 3 zeros and 4 poles. The distribution of its zeros and poles in the plane S is shown in the figure. We can see that its 4 poles and 2 of its zeros are close to the imaginary axis. They're located in the frequency of omega equals 2, omega equals 6, and omega equals 10, respectively. The other zero is real and rather far from the imaginary axis. What kind of amplitude frequency response will this system have? From its amplitude frequency response graph, we can see that there are peaks at omega equals 2 and omega equals 10, and a valley at omega equals 6. In practice, we can design a filter roughly based on the principle above by setting zeros and poles in the S-plane properly. For instance, we have designed a filter as above. Its filter, in fact, can be illustrated by another example. A signal f of t, which contains 3 frequency components, omega equals 2, omega equals 6, and omega equals 10, is inputted to this system. Let's see what happens to the signal spectrum before and after passing this system. This is the spectrum of f of t, which is the spectrum of the signal before passing through the system. It contains 3 frequency components. After passing through this system, the components of omega equals 2 and omega equals 10 remain unchanged, while the components of omega equals 6 is suppressed, or in a sense, the component of omega equals 6 is removed. Now, let's go to the discrete LTI system to inspect the relation between its frequency response and the distribution of its zeros and poles. The necessary and sufficient condition for the causal stability of the discrete LTI system is that all the poles of its system function are located within the unit circle of the plane Z. In this case, the frequency response of the discrete system can be obtained by replacing the Z in its system function with the e to the power of j omega. Therefore, for a discrete LTI system, the features of its amplitude frequency response and phase frequency response also depend on the zeros and poles of its system function. The relation between the frequency response and the zeros and poles can be analyzed in a manner similar to previous continuous system. We build zero vectors and pole vectors respectively for each zero and pole of the system function. Then, the amplitude frequency response of this system depends on the module of its zero and pole vectors, and the phase frequency response depends on the phase angles of its zeros and pole vectors. Such a result is similar to a continuous LTI system. We can also adopt the same method as the continuous system to analyze the influence of zero and pole positions in the plane Z on the frequency response of a discrete system. But there are several discrepancies between discrete and continuous system that we should notice. Firstly, the imaginary axis of the plane S is mapped to the unit circle of the plane Z, and the left half of the plane S is mapped to the area within the unit circle of the plane Z. Secondly, the angular frequency omega of the discrete system rotates counterclockwise around the origin with a period of 2 pi. Thirdly, mirror symmetry about the imaginary axis in the plane S is mapped to a mirror symmetry about the unit circle in the plane Z. For example, the pole P1 within the unit circle has a mirror symmetrical 0, zeta 1 outside the unit circle. Fourthly, the ratio of the vector modules of a 0 to its mirror symmetrical pole is a constant and does not equal to 0. Finally, let's summarize this lesson. Firstly, the frequency response of continuous or discrete LTI system is closely related to the parameters of its system model, which means the zeros and poles of its system function. Secondly, according to the zero and pole distribution of its system function, we can roughly and qualitatively evaluate the amplitude frequency response of this system. Thirdly, we can also roughly design a filter with certain amplitude frequency response characteristics by setting zeros and poles at appropriate positions in the S or Z plane. That's all for today. Bye.